Hi everyone, we are Chordly, the CS4100 final project.
I'm Nalini.
I'm Hollis.
I'm William.
I'm Mayor. So let's talk a little bit about our motivation. So we decided to do a little bit into music theory. So that's a study of practicing how chords, scales, rhythm, and harmony all kind of work together. The reason we chose this is because we're all interested in music, but William and Mahalis are musicians themselves. And this gave a really deep personal connection to actually make something meaningful. Now, the solution that we had was that we wanted an AI-powered system to actually generate these chord progressions. The input would take a key and a scale. The output would take a sequence of these chords and produce a MIDI file. Very simple. Now, there's some issues with this, making sure that all of them are harmonically valid. There was variety, such as no repeats, and balancing the algorithm for theoretical correctness to creativity, because at the end of the day, music is about creativity.
So yeah, awesome. I'll jump into the first model, which is our Markov model. Basically, we have a couple functions here, the train and generate function. We're essentially grabbing the current chord and comparing it against the following chord, tracking transitions across all the chords as a dictionary, and then an inner dictionary tracks all the other counts. So we have regular counts, and then we normalize them into probabilities for the generation portion. And with that said, I'll transition to William.
The next model we used was a genetic algorithm. The two operators we used are show and mutation, which randomly swaps a chord, and crossover, which combines two parent progressions. The fitness function, not shown, rewards chord transitions that appear frequently in the input data, and the progressions evolve over generations to produce coherent sequences. The third model we used was the LSTM, which was a PyTorch import, given that we already had two handwritten models, sort of kind of as a baseline and or frame of reference to compare against our hand-built models. And LSTM models in general are advanced variants of recurring neural networks, which are much better at learning long-term relations, which are very important in music theory.
For the audio generation, the models output Roman numerals, which are converted to MIDI files, and then we use FluidSynth to convert it into a wave audio. And you can choose between six instruments, and all of this is in the backend, so the front end just has to call endpoint.
Awesome. Now that we talked about this in theory, let's actually see the demo. The user would just click the generate button and produce this. Beautiful music. And I'll play a little bit over here so that you know it goes all the way. Amazing. So now we can audibly hear it. Visually, we can see the statistics over here. We can also see the progression, which is outlined over here. We can change the model from all these kind of different things. I'll show in a bit. We have a dark mode, and we also have a compare function, so we can see two different ones. We have a genetic algorithm, the Markov, LCM, completely different instruments, keys, lengths, and data sets. And as well, every time that we look for a model, it'll also explain a little bit about what the model does. In the interest of time, we're going to go back to the slides.
Awesome. So we'll start with the data analysis. For some context, the data in this case was a huge list of chord progressions from all sorts of different music. Music, after all, can be condensed into chord progressions, and those chord progressions can also be made back into music. So we used a text file that William made and analyzed it here. So we'll go from left to right. Entropy in this case, we're only comparing Markov and LSTM because these two work with probabilities. Markov, in this case, has a higher entropy, meaning it is more diverse in what it's producing, a little more random. On the right side, we have GA fitness over time. So as you can see, there's a pretty steady trend upward, meaning that we train our model very well on the data, and we got a pretty successful output as indicated by the recordings. And now for the next slide. So yeah, on the left side, we have chord frequency. We're essentially comparing how often chords appear for major and minor chords. As you can see, LSTM likes to favor the chord 6 in both versions of 1, while the other two models tend to be a little more leveled out, especially Markov. On the right side, we have a little more model metrics to compare, diversity, repetition, and transition validity. Diversity is kind of what I implied before. As we can see, Markov is a little more diverse, GA is right in the middle, and then diversity for LSTM is right at the bottom. A repetition, LSTM is at top, and then transition validity is just how well the chords are progressing through the other chords. So it's pretty static throughout, so there's no change there. And now for the final slide. So yeah, takeaways from the data analysis. What we were able to decide was that Markov produced the most diverse results, drawing from a wide array of chord numerals. LSTM, on the other hand, was right at the bottom of all of our statistics. It is not only the least diverse, but also extremely repetitive, repeating chords such as 1 and 6. And GA kind of fell between the two, right smack dab in the middle. So it was pretty fair, but Markov proved to have the most successful results for us in the long run.
Awesome. And the conclusion is that while we worked a lot with the data, it was amazing to see that we had a theoretical algorithm that was correct and turned it and trained the AI to make something very creative, which is absolutely amazing. Thank you so much for listening, and thank you, TAs, for helping us in this process. Done.